So now that we have that out of the way, let's start talking about how we can, as good scientists, describe the properties of this wave. If you were to start asking questions about this wave, or if you were to be a good scientist and try to measure things about the wave, what would you measure? What questions would you ask? You might want to know things like, how fast is the wave moving? How much are the particles oscillating? How much energy is there in the system? Things like that. So we're going to start talking about some of those properties. Okay, so how can we describe waves? Well, first of all, we need to talk about this idea known as equilibrium position. This is the position the particles would, would take if there were no energy passing through the system at all. So let me give you some examples of what I mean by equilibrium position. This is the equilibrium position of the string. You can see that no energy is passing through. It's just sitting there. No change has been caused in it. It does not have the potential to cause a change. No energy has been added. No energy is passing through. It's at equilibrium. As soon, though, as I add some energy, it starts to oscillate. And there I have some oscillations, right? So I have deviated the particles away from their equilibrium position. The dotted line would represent the equilibrium position. I have deviated the particles away from the equilibrium position. And after a time, the energy will dissipate into the surroundings, and the string is at equilibrium position once again. The pendulum, that's still swinging. If I turn on friction, energy will start to dissipate out of the system as thermal energy, as heat, and eventually I'm going to see the pendulum do what? It's just going to hang straight down and come to rest at its equilibrium position. How about the spring with masses? Well, you can see that the spring with nothing on it, nothing affecting it, it's already at its equilibrium position. I am causing the spring to deviate away from its equilibrium position in a rhythmic, patterned way. So the idea of an equilibrium position is where the particles of the medium would be if there was no energy passing through the system at all. What a wave does is it adds energy and causes the particles to oscillate or vibrate away from their equilibrium position. Amplitude is the distance away from equilibrium. I'm going to say actually the maximum distance away from equilibrium which a particle has due to oscillations. The maximum distance away from equilibrium which a particle has due to oscillations. A much simpler way of saying that is the height of the wave. How tall is the wave? So here's the idea of amplitude. Let's say that I have a string or something and I'm wiggling it around, I'm waving it around. Here you can see the resting position or the equilibrium position right here. So I'm shaking the string up and down, the particles are oscillating up and down, the wave energy is moving left to right, it's a transverse wave. Well, you can see that the maximum distance that a particle moves away from the resting or the equilibrium position is defined as the amplitude. That's something I can measure. It's a length I can measure. It would be measured in something like centimeters or meters, depending on the object. Over here, you can see the same thing. These blue arrows represent the amplitude. How high is the wave? Now, here's a common mistake that is made when people are measuring or talking about amplitude. They are often tempted to measure from the very top of the wave to the very bottom of the wave. By the way, those tops and bottoms have specific names. We call them peaks, are the top of the wave, and troughs, the bottom of the wave. Sometimes we call the peaks crests instead. That's also an acceptable term. So sometimes people will claim that the amplitude of a wave is measured from the peak to a trough, all the way up here to all the way down here. That's incorrect. Remember what I said the definition of amplitude was. It is the distance, the maximum distance, away from the equilibrium position. So you could measure up to a crest or down to a trough. That would be the amplitude. However, if you measure up from a crest all the way down to a trough at one time, that would technically be twice the amplitude. The amplitude tells you how far away the particle is at maximum from equilibrium position, from where it would normally be if there was no wave energy passing through. Does that make sense? Amplitude, it turns out, is related to the energy in the wave. I think this is not difficult to understand. Over here on the left, that's a low energy wave. Over here on the right, that's a high energy wave. How do these two waves differ? Their amplitude, right? The one on the right, the high energy wave, has a much higher amplitude. I think that makes pretty good common sense. If I wiggle this around with just a little bit of energy, you can see that the amplitude is very, very small. These particles do not deviate much at all from their equilibrium position. However, if I put lots of energy in, then the amplitude is much bigger now. These particles are deviating quite a bit from their equilibrium position. Does that make sense? I can change the amplitude of this. So if I decrease the amplitude, you can see the waves are getting shorter. And this machine is putting less energy into the system. However, if I increase the amplitude, the waves get taller. I mean, look at the green dot. The green dot is deviating so far. The green dot's deviating so far away from its equilibrium position. That's the amplitude. Again, whenever a wave is at its maximum height above equilibrium position, we call that the peak. When it's at its maximum distance below the equilibrium position, we call it a trough. You can see that in a wave system, because it's dynamic, energy is passing through. This is a transverse wave. The peaks and the troughs are moving all the time. A peak will become a trough will become a peak because the wave is moving. That's how it works, right? So amplitude is the height away from the equilibrium position, and it's related to the amount of energy in the wave. Now I do need to kind of back up and give you some more vocabulary. I think it's very easy to identify peaks and troughs, but what about for a longitudinal wave? How do we talk about peaks and troughs? Because it's not going up and down. The particles are not moving up and down. They're moving side to side. Well, we don't use the word peak and trough to describe longitudinal waves. Instead, we use the words compression and rarefaction. A compression would be like the longitudinal equivalent of a peak or a crest. A compression is where the particles are close together. Compression. A rarefaction is where the particles are spread far apart. That would be like a trough. So for longitudinal waves, we do not use the term peak and trough, or crest and trough. Instead, we use the terms compression and rarefaction, where compression means the particles are colliding with each other very close together, and rarefaction represents where the particles are spread out. So amplitude is the height of the wave, once again measured away from the equilibrium position, and it's related to the amount of energy in the wave. Frequency. This is an incredibly important property of a wave. Frequency is the number of wave cycles passing through the substance each second. Frequency is the number of wave cycles passing through the substance each second. So let me come back over here to my wave on a string simulation. You can see that I can change the frequency. Basically, the frequency, if I increase it, is going to cause my machine to put more waves per second. So let's see what happens if I increase the frequency. You can see that this machine on the left side, the thing that's putting the energy in, is starting to oscillate faster and faster and faster. And so I have more waves passing through every single second. So the frequency would be the number of complete wave cycles passing through a substance every second. If I decrease the frequency, you can see I'm going to have much fewer waves passing through. Wait for it to kind of equilibrate with itself. That's an incredibly low frequency, right? Let me go up a little bit higher. There we go. So there's a low frequency. There's a high frequency. It's important that you understand how we measure frequency. Frequency is measured with a unit called the hertz, which we abbreviate Hz. 1 hertz is equal to 1 wave passing each second, 1 wave per second. In other words, a hertz, the unit of a hertz is 1 over seconds, 1 over s. It could also be described as s to the negative first power, if you know your math. If that doesn't make sense to you, don't worry about it. It is important, though, that you understand that frequency is measured in hertz, where a hertz is basically the unit per second. How many waves per second are passing through? Please make note that frequency will tell you how many complete wave cycles are passing per second. It is possible to have a fractional frequency if you have 2.5 waves passing or something. So how do we define what is a whole wave versus what is a half wave? A wave cycle is defined as one complete back and forth oscillation, basically. So up, down, and back, that's defined as one complete wave cycle. So let's imagine this. Look at this wave system. Imagine that this passed by in 1 second. What would the frequency of the wave be? So if this is passing by in 1 second, remember frequency is the number of complete wave cycles that pass every single second. So I see 1 wave cycle, 2 wave cycles, 3 wave cycles. If that passes by in 1 second, the frequency of this wave would be 3 hertz, 3 waves per second. Period is the reciprocal of frequency. What that means, in other words, if frequency is the number of waves per second, period is, you just flip it. Period is the number of seconds required for 1 wave to pass. In other words, how much time that it takes for 1 wave to pass. So I want you to think about this. If 3 waves pass every single second, how many seconds would be required for 1 wave cycle to be completed? A third, right? 1/3, 0.33333. If 1, 2, 3 waves pass every second, the frequency is 3 hertz, then you just flip that number. 3 over 1 becomes 1 over 3, and that's going to give you the period of the wave, how much time is required. How many seconds does it take for 1 wave to pass? Well, if 3 of them pass in 1 second, it's only going to take 1/3 of a second for 1 wave cycle to pass, for example. So we can get an equation for period. Period is given by capital T, that's the abbreviation for period. And period is always going to equal 1 over f, 1 over the frequency. Frequency, by the way, is abbreviated with an F. Period is abbreviated with a T. And what unit do we use to measure period? We use seconds, right? Because it's time. How much time does it take? So frequency and period are very closely related to each other now.